So it's time to start a slightly different type of equilibrium problem. The types that we've seen so far, you're given initial concentrations. You're kind of told what the change to those concentrations are going to be, so you can calculate what the equilibrium concentrations are. We would then take those equilibrium concentrations, plug them into a Kc calculation, and generate at the end a Kc value. So they define the change, and you calculate Kc. We're going to take these problems now and kind of turn them around, spin them around a little bit. The change to the concentration is not going to be defined, but we are going to be given the Kc value, and we're going to have to somehow from this calculate what our equilibrium concentrations would be. We're going to go through two examples through this video. We're going to look at example number 6 and example number 7 from your in-class packet. So make sure that that's out and in front of you. Here's problem number 6. So we have a lovely equilibrium equation down at the bottom. We're given the Kc value of 3.0, and we're also given initial concentrations for 2 of our reactants, 1 mole of each of them, but this time they're in a 2-liter container. Remember that you do need to know the concentration, so you'll simply take the moles divided by the liters for those particular lovely problems. Now, since this is an equilibrium problem, we're going to go back and look at that world according to Donovan chart type problem, and let's set one up now. So here's my chart problem for this particular equation. You can see I have my reactants and my product set up, and then initial change to concentration, and then finally those final equilibrium concentrations given. I'm going to layer in the information that I'm given in the problem. And that is simply this, that I have a starting concentration of 0.500 molar in both SO2 and NO2, and I can assume, because I wasn't told anything about them, that my initial concentration of both of my products is 0. And we're not really told a whole bunch more than that. The other thing that I do like to do in these problems, if I know that I'm given a Kc and a Kc value, I like to define what my Kc looks like, just that I know where I'm headed with my problem. In this case, again, as always, it's the concentrations of the products divided by the concentrations of the reactants. And I would love to plug and chug some numbers in there, but I don't have anything to work with yet. So you'll notice I basically have the whole skeleton of the problem done here. I just don't know what my change is. And unfortunately, this time, that's what the variable in this problem is going to be. So let's define our change as x. What you'll also notice is that if I have reactants but I don't have any products, there's essentially only one way, one direction for this equilibrium to shift. It is going to shift toward my product side. So as I'm defining my change to concentration, all of the reactants are going to reflect a negative change, and all of my products should be reflecting a positive change. So when I fill that into my chart, I'm going to fill in 2 negative x's for my SO2 and my NO2 concentration, and 2 positive x's for my SO3 and my NO concentration. And then simple math down to try and fill in what my final concentrations would be at equilibrium. I would have 0.500 minus x for both SO2 and NO2, and then just 2 x's for SO3 and NO. And at this point, it's really just a very large algebra problem, where you're going to plug and chug those equilibrium concentrations back into my Kc calculation. And that's what this is going to look like. So I would have x times x divided by 0.500 minus x, and times 0.500 minus x. That's all going to equal 3. So I just want to simplify this, clean this up a little bit. I'm going to be left with 3 equals x times x, and then the stuff on the bottom as well. And I can clean that up again even further and make that look like this. X squared divided by 0.500 minus x squared. The most simplest path forward with algebra would be to square root both sides. That'll knock out both of your squareds and should make the algebra part of this a little bit easier. I'll leave you to do that. I'll just simply tell you what the x value is. So while you work on the algebra, you should probably pause the video, and then when you're ready to continue, just hit play again. So I found x to equal 0.184. That would be 0.184 molar as the change to the concentration. Now, just so you know, the AP people at this point would not consider this problem finished. They asked for the equilibrium concentrations. So you're going to need to give that to them in a very big and bold way. I usually make sure I define everything and then circle it if I had a highlighter, I would highlight it on the page. And that would look like this, where I say that my concentration of SO2 equals the concentration of NO2, and both of those are equal to 0.316 molar. That would be my 0.500 minus the X value that I could plug in. And then my SO3 value and my NO value are equal to each other, and those both equal 0.184 molar. Now this is a fairly straightforward example. I didn't have any coefficients, any stoichiometry to worry about. It was really just a plug and chug problem. So I do want to run through one more that's a little bit more complex, and that would be example problem 7. And here it is. So it's the same scenario. They're giving us the Kc value of 49 at the beginning of the chemical reaction. And they're saying, I'm going to put in 1 mole of HI into a 1 liter container, and what are the concentrations at equilibrium? Again, they give us Kc, but they do not define what the change to the concentration is. And it really doesn't matter. All of these problems start the same way. You instantly want to define what Kc looks like, and you want to develop a chart problem underneath your equation. So I started that work here. So here's my equation in my chart problem. And then I very quickly define what I'm initially given. I know if I have 1 mole of my HI and it's in a 1 liter container, then my concentration must be 1 molar. I also know that I was not given any information about my 2 reactants, so I'm assuming that their concentrations begin as 0. I'm going to define in this problem my change in concentration as negative X, and that's simply because I do know that if I have all product and no reactant, my equilibrium is going to shift back toward the reactant side. So I'm always going to say that that side is now negative X. My product is going to change by X. So let's now think about this. You have a different multimole ratio. You have 2 HI. That's going to equal your H2 and your I2. So stoichiometrically, we do need to apply that ratio. That will be a 1 to 2 ratio to try and get to what our change in concentration would be to keep it proportional. So it's actually going to end up being plus 0.50 x's for both the H2 and the I2. And if you don't believe me, sit down and write out that stoichiometry. Start with your HI and convert it to either H2 or I2, and you'll see it's basically a factor of 1/2. Now we can define our equilibrium concentrations, and of course they're going to have X in them, and we still need to clean that up in the back end. So 0.50x for both H2 and I2, and then 1.00 minus X for my HI. Let's go ahead and define that Kc value. So we do Kc equals 49, and again, here's the number one source of error, and it's actually in knocking out what this lovely Kc calculation would be. Notice on the top there specifically, HI squared. That's the part that's going to get forgotten by most people, divided by H2 times I2, product over reactant. We can start to fill in with a little bit more additional information. So that would be 1.00 minus X squared divided by 0.50x times 0.50x. Again, we can start to clean up that equation and start to work toward algebra and solving. So I simplified it to 49 equals 1.00 minus x squared divided by 0.50x squared. Again, algebraically, what I would do here is square root both sides to get rid of those squareds. So you would have 7 equals 1 minus x divided by 0.50x. And then it's some simple algebra to solve for x. Again, I'll let you kind of go through that. You might want to pause the video at this point, work through your algebra, and make sure that you come up with the same answer that I'm about to. I found that x equals 0.22 molar, so that's just the x value. That's not necessarily what all of the change is equal to. I still need to plug that value back into my chart problem up top to define what my final concentrations are. And I found that I2 and H2 would be the same, and that would be roughly equal to 0.11 molar, and that my HI concentration should be equal to 0.79 molar. Although these problems are not necessarily super difficult, they can be a little tedious. You should be exceptionally careful to make sure that you're defining your change to the concentration with respect to those coefficients up top. And don't forget to include those coefficients in your KC calculations as those exponents. It does count in both places. That's, I think, the most difficult thing to get used to. So good luck, get those homework problems done, and I'll see you in the next video.